Alright, so here's example 4 with related rates. So if you want a copy of this worksheet here, check the video description and you'll find a link there that'll take you to a place where you can download this, you save it on your computer, you can print it if you want, and then follow along with the video. So anyway, example 4, let's zoom in a little bit. So here, a large spherical balloon is being inflated and its volume is increasing at a rate of 3.5 cubic feet per minute, and we want to know what is the rate of change of the radius when it, meaning the radius, is 7 feet. Alright, so we read the question. Now let's go to our general process here. Step 1, draw and label a picture if possible. So it is possible in this case, but it's probably not going to be very helpful. So, you know, we just have a spherical balloon that's being inflated. So sphere, and then here's the radius, which we'll just call little r. And you know, the volume here is increasing at a rate of 3.5 cubic feet per minute, but that's not really something to label on a picture here. But anyway, that's it for step 1, draw and label a picture. So step 2, using mathematical notation, make a list of what you are given and what you want to know. So what are we given? Well, we're given that this balloon is being inflated and its volume is increasing at a rate of 3.5 cubic feet per minute. So if we let big V be the volume, then dV dt, okay, that's the rate of change of the volume, and that's going to be 3.5 cubic feet per minute. Alright, and it's a positive rate because, you know, the balloon is being inflated, so its volume is increasing. Okay, because the volume, big V, okay, we're using big V for the volume, because that's increasing, then dV dt should be positive. Okay, because it has a positive rate of change because V is increasing. Alright, so that's what we're given. We're not really given much else, and what do we want? We want to know the rate of change of the radius when it, meaning the radius, is 7 feet. So we want, little r is representing the radius, so we want the rate of change of the radius, which is dr dt, when r is 7 feet. Alright, so that's it for step 2. Using mathematical notation, make a list of what you are given and what you want to know. Now we go to step 3. Once the focus fixes. Okay. Step 3, write down the relevant equations, and they're usually going to be geometric formulas. So step 3, what are we dealing with here? We're dealing with a spherical balloon, and we're talking about the volume of the balloon and the radius here, right? So, you know, we should probably use the formula for the volume of a sphere, which is big V equals 4/3 pi r cubed. Alright, so there are other formulas that are related to spheres, right, like the surface area formula, but that's not relevant here because we're not talking about surface area at all. We're just talking about the volume and the radius here. So, you know, if we think about it, we'll think, oh, okay, volume and radius, so let's use this formula here. So that's actually it for step 3. Write down the relevant equations. So now step 4, implicitly differentiate both sides of the appropriate equation with respect to time. So we're just going to take this equation here and implicitly differentiate with respect to t. So v, when we differentiate with respect to t, we just get dv dt. So dv dt. And then what happens on the right-hand side? 4/3 pi is just a constant multiple, so it stays there. Okay, when you take a derivative with the constant multiple is just going to stay there. And then r cubed. So this is going to be implicit differentiation, and then that's just the chain rule, right? So r implicitly is a function of t, and then we cube it, right? So what we have here is a function inside of another function. So r is already a function, and then inside it's going to be inside of this cubing function here. So a function of t, and then it's being cubed. So the chain rule says the derivative of that is going to be the derivative of the big guy evaluated at the little guy. So that's going to give us 3r squared. Okay, the 3 and the squared, those are the derivative, that's the derivative of the big guy, because the big guy is cubing. So 3 is squared, that's from the big derivative of the big guy, and then evaluated at the little guy, so that's r. And then multiply by the derivative of the little guy, so that's dr dt. Alright, so again, r cubed, if we implicitly differentiate with respect to t, we just get 3r squared dr dt. Alright, so then 3's cancel, and then we have dv dt equals 4 pi r squared dr dt. All right, so that's it for step 4, implicitly differentiate both sides of the appropriate equation with respect to time. And then step 5, plug in the known quantities and solve for the unknown variable. All right, and in this case, the unknown variable is dr dt. So we know dv dt, right? It's given to us. It's just this constant right here. And we know this is happening when r is 7. So this is an important thing to point out here. R equals 7. The radius little r, it's not really constant, right? It's not a constant 7, so we can't plug that in the beginning. R is a variable, and we want to know stuff about this other variable when this variable has this specific value. Okay, so because little r isn't always 7 feet, then we can't plug this in until we have taken the derivative, right? So unless something is a constant, you can't plug it in until after you've done the derivative. So yeah, this here is a constant, right? But this is a derivative, so we can't even use it until we have derivatives. But you know, if you think back to example 1, you know, we had a 17-foot ladder, right? So in that example 1, with the 17-foot ladder, we can plug that in from the very beginning. But here we can't do this kind of thing here because the radius of the balloon isn't always 7 feet. The radius is changing. So for quantities that are changing, you have to wait until after you've taken the derivative to plug them in. All right. So that's okay to do that now, okay? Because here, when you're taking the derivative, it represents what's happening at a very specific instance, and we want to know what's happening with dr dt at the specific instance when r is 7 feet. So that's why we have to wait until we've taken the derivative to plug in r equals 7. But anyway, now we can do that. So if let's come up here where there's more room. So dv dt equals 4 pi r squared dr dt. All right. So we want dr dt when r equals 7, and we know dv dt is always 3.5. So 3.5 equals 4 pi times r is 7, so r squared is going to be 7 times 7, all right, or in other words 49, but there's a reason I'm leaving it like that. So then dr dt. All right, so now we just divide both sides by 4 pi times 7 again. 4 pi times 7 times 7. So these cancel, and then dr dt is left by itself. So let's come back up here now. And then we have dr dt by itself on one side of the equation, and then on the other side we have 3.5 over 4 pi times 7 times 7. So 3.5 over 4 pi times 7 times 7. So now 3.5 goes into 7 twice, because 3.5 times 2 is 7, right? So that's why I left these 7 separate, but you know, you didn't really have to do that, because if you have a calculator handy, you could just simplify it anyway. But, so anyway, now we have a 1 on top, so dr dt equals 1 over 4 pi times 7 times 2, so that's going to be 56 pi. All right, 1 over 56 pi. And then what are the units? Well, here, the volume, the units on the rate of change of the volume, that's cubic feet per minute. So the radius, dr dt is going to have just feet per minute. Because the volume is cubic feet and the rate of change is per minute. So radius, that's just feet, and then its rate of change is also going to be per minute. All right, so that's that. Now, if we wanted to approximate that, we can toss that into a calculator, and we'll see that this is about equal to 0.005684 feet per minute, which is actually not very quick, right? This is it's a pretty slow rate of increase, which you might kind of expect. So, you know, if you think about it, you got this big old balloon here, it's being inflated, and you want to know how fast is the radius changing when the radius is 7 feet. So if the radius is 7 feet, that's a pretty big balloon, right? And if you're pumping in air at this constant rate of 3.5 cubic feet per minute, you know, so the volume is increasing at this constant rate. So as the radius gets larger and larger, you know, the rate of change of the radius is it's still going to be increasing, right? The rate of change is still going to be positive, but it's just going to be getting smaller and smaller as the radius gets larger. So anyway, that's what's going on here. All right, so that's it for example 4 with rate of change.